So with all that said, let's start with introducing Spark. Well, the core concepts behind Spark are the following. We have some specs and we have some repository. Repository explains the knowledge about installation of the software. And this knowledge is presented by some Python scripts. I will show you example later on. So basically, consider repository as some knowledge base about installation process. Specs, you can consider specs like some formulas which allow you to create queries for installation. Then one of the internal and central parts of the Spark is the so-called concretizer. Concretizer is the tool which allows from some spec create a directed acyclic graph of dependencies of this spec. So it allows to assign some concrete versions, to define the whole process of installation in details, and also concretize it for all dependencies. While Spack is written in Python, the core of Spack is written in Python. Well, concretizer is, Spack has some internal concretizer, but it is also possible to use some external concretizers for Spack. That's some topic which is beyond the scope of this presentation, but in general, it is possible. And Spack has CLI, command line interface. So the typical workflow for the users, users prepare specs or environments based on specs. Then they call CLI, command line interface, and command line interface then communicate with core Python library of Spack, and this core Python library uses a repository of package.py script to respond to the user's requests. So now, what is Spec? Spec is some simple definition, some simple query to for the installation. In this slide, you have a few examples of the Spec. So in the simplest way, you can just tell Spack, just use the Spec, which is the name of the package which you want to install. But actually, specs can be more elaborated. They can include versions. They allow to define versions. They allow to define concrete dependencies. They allow to define compilers with which you want to compile your software or dependencies and so on. So all installed packages can be referred also by hash, by a unique hash, which is basically one of the simplest way to referring to the external packages, and without any ambiguity. So, for example, here I show that on my system there were two packages, readline with the same version, readline 8.0. So if you will use in the dependency, if you will define the spec readline 8.0, it won't be clear which 8.0 will be used out of these two. And you can refer to these read zeros by hash. For example, here, the hash is FEQ and so on. So, and you can refer to this hash by this, to this dependency by this definition of hash. So now the question is how to construct spec. What can we use as package names? What can be used by as other elements of the spec? So for package names, in order to know what package names can be used, you can simply use the instruction Spack list, which lists all the packages by default. But you can also make some queries to the Spack list, more elaborate queries. For example, here, the query which asks Python to list all packages which have pyth in their name, and here we ask Spack to look for not only by name of the package, but also by the description of the package. It's something like apt-cache search, if you know about this. This part of apt package manager. So then when we come to the tools such as Python, they usually use some packages as well. So such as NumPy and so on. So they are extensible with some packages. And in order to look for extensions, a better way is to use the instruction. You can still use Spack list, but the better way is to use Spack extensions utility. And this, by default, this Spack extensions call lists you all available extensions. And if you will call Spack extensions with some particular package, extensible package, and you tell it list only packages, then it will show you the output with all the packages. And as you can see, for Python, for example, in the Spack 0.16, we had already more than 1,000 packages supported by this package manager, Python packages. So now let's go to the next components of the Spec: versions and compilers. Versions can be viewed. You can check versions with the instruction Spack versions. You can also see versions with Spack list, and this particular call provides you a bit more details than simply versions list. It provides you quite elaborate information about available configuration of the packages which have MPI within their names. So with the compilers, here is how to get to know what compilers can be used. So you can simply list available compilers with list compilers, and you can get the information about the compiler which you want to apply to some installation in Spack with Spack compiler info, and then that's basically, here should stand a spec which corresponds to the compilers which you are interested in. So now how to how about configuring packages when we are install something? So Spack installs everything from sources. Therefore, you have a full control on the configuration of the packages you install. And well, basically, this control is granted in several ways. First of all, you can use flags, but this is not a recommended option. The much more safe version is to use so-called variants. Variants is some additional information on the configuration which you want to use with the spec. And you can check all variants with the call Spack info and then the name of the package which you want to know about. And with this Spack info call, you get much more than simply a list of variants. You get the description of the package, you get the information about all versions and where the sources for these versions are pulled from, fetched from. Then you also get the information about variants and what are default values of these variants and what are allowed values actually for these variants. Then you also get information about installation phases for this particular package and the tools, the dependencies for each of these for these installation phases. So. And now one more thing, it's important for constructing specs, it's the concept of virtual packages. As you know, MPI is actually not a package. It's some standard, some API, and Spack also allows to define virtual packages, which are basically some not the real package, not real packages, but some API specification. So if you want to take a look on the supported virtual packages, you can call Spack providers. And one of these packages, for example, MPI, but it has many more, which you probably use, such as BLAS and so on, or Java. If you want to know which packages can be used for this interface, for these virtual packages, real packages, which are installable, you can use Spack providers with the name of this of the interface which you are interested in. And for example, here is a list of packages which are supported by Spack for MPI. So, and the last stuff is that you can also specify a platform for which you want to compile the package, and there are many options. You can which allows you to check what platform is actually by default Spack will use, and which platform does it recognize. And Spack has this ability to check for both front-end nodes and back-end nodes. So, and it allows to get also parts of the platform definition, such as operating system or the target microarchitecture. And if you want to know about supported microarchitectures, you can call Spack arc with this option, known targets. So now the second concept important for Spack, it's packages. Packages, as I've told already, packages are simply Python scripts, and here is an example of one. In the package files, you basically have to define a class which inherits from some Spack predefined classes. And in this class, you will define the command which will be used later on in the Spack info as an information about the package. Then you have to define homepage for the project, URL for the project, the maintainer for the project, and versions of the source tarballs or codes which are supported by this package. And usually you should also take care about, but this list of versions is created, actually filled in by Spack itself with one of the supported commands. So you don't have to take care on preparing this versions list, Spack will take care of about it instead of you. So then you have to define variants, and basically here in this package I define variant that this package can contain shared libraries or not. Then it can be built with release or debug mode. That it can use some osmium, some external library tuning, and this library is called osmium. Then it supports Doxygen or not. If you don't aware about Doxygen, it's just a generator for the documentation, and it supports Proto0 library or not. So, and yeah, afterwards you have a dependency section where you define what this package depends on, and in which step of the installation process it depends on some particular package. For example, here my package depends on the build phase. My package depends on binutils. pkg config and cmake and git. But these packages are not required for in other steps, only for build. Here are some dependencies which are actually required also for linking. By default, yeah, if you do not tell that it is for build, particularly, it will also be considered as required for linking. And you can also here make some filtering, for example, filtering depending on variants. For example, if I want to install my package with Osmium library support, then of course, I should define dependency on the Osmium library. Same with Doxygen support, I should define dependency on Doxygen and so on. So you can also, after dependencies, you can also define some conflicts. For this particular library, which I wrote the package for, called Lipo SRM, this library requires C++ 14, and C++ 14 was fully supported since GCC 5.0, if you use GCC for compilation. And if you have a GCC of previous versions, this will generate a conflict, generate an error message if you will try to install this library from sources. And afterwards, you can also define some additional tunes for the installations by means of some methods. For example, here I define some requirements to set up the build environment before installing the software. For example, in this case, I define some environment variables. These two lines were added just for an example purpose, but you can simply avoid them because Spack will automatically take care about these libraries which are related to external dependencies by themselves. And now here I define some additional arguments for CMake in this particular example. And for example, I tell CMake to compile it to compile my library as shared library if I define the variant plus shared. Okay, so that's packages. So now let's go to Spack. We have the core concepts now, how to use them. So if you want to install packages, you should use the command Spack install. And this command has a lot of different options, which cover basically almost everything which is supported by state-of-the-art package management tools. But it has some more stuff. For example, it has some options for support of the external mirrors. It has some options for support of the tests after installation of the software. And it has support of logs when you install some software. In particular, Spack is integrated with C-, and if you want, you can use a graphic interface to see how the installation process is going on. So next thing, but as we all know, if you install from sources, there are high chances that there will be some error, at least if the installation process is not tested well enough. And in order to find the mistakes during the installation process, Spack has a lot of debug options. But that's not enough sometimes. And in order to fix the issues which arise, you need to know installation process in more details. So the installation usually includes the following steps: concretization, installation of dependencies, staging, creating build directories, then the core installation process, which is configuring, building, and installation of the software from sources, and then cleaning up build directory and removing the stage. So what out of these all can fail? Basically, almost everything, but the highest chances to fail are for concretization, for installation of dependencies, for building process. Less error-prone part is staging, and there are almost no chances that creating build directory or cleaning up build directory will fail. And now let's go through these error-prone parts. The first part is concretization. Well, before installation, you can always check how your packages will be concretized. In order to do it, Spack has a command Spack spec. And basically, here I show you the output of the Spack spec with options L, I, T, and the name and the spec itself, which is the name of the package in this case, librsrm. So, and in this output, as you can see, you see the whole installation tree. If everything is fine, you have the whole installation tree. You have information. First of all, you have information on which package is already installed, which is not. For example, in this case, this particular spec librsrm was already installed, and you have an installation which repository of package.py files was used for installing this spec, and you have details on how Spack concretized this particular spec. And the same story for all dependencies of this spec. You have, for example, here you see that we have dependency xz, and you have this information that it was also installed. You see its hash, and you see what this dependency is used in. In this case, it's used for building, linking, and running librsrm library. And yeah, let's go to the next stuff. How to solve the problems if command Spack spec does not execute successfully. So basically we have, in this case, we have some concretization problems. So the first stuff you have to do is to try to change the spec. Basically, to try to find what combination of dependencies work well. And if you have found the proper combination of dependencies, it is not mandatory, but it is recommended to fill this knowledge to the package.py, to store this knowledge to the package.py script. So other users, when they will try to install, they will not ever face the same problem. So the next stuff which you can do is to play with option C and cover of the Spack spec, which allows you to build DAG of dependencies in a different way, like probably a little bit more elaborate way. And finally, if it doesn't help either, you can use external concretizers, for example, CleanGo. And here is a way how you can install CleanGo and make it run in Spack. So yeah, and the last resort is again going to a package.py file and trying to modify it directly without changing spec, but with some hand waving. Let's go to the next opportunity for failing. If we have failing dependency, so how to check which dependency fails? The easiest way is to call Spack install with fast installation and with dependencies only installation. And when something will fail, what to do in this case? The answer is simple. You should find the name of the failed package, spec of the failed package, and go to that package and try to install it. first to make installation of that particular package running. So now the next problem, possible problem, if we install the package and that package fails in some configuring, building, or installation phase. So what can we do? The first thing you have to do is to install dependencies and to stage the package and switch to that package folder. That can be done with these 3 commands. Then you can try to fix the issue with config build install in a common manual way. And then you can modify Python.py. As soon as you know what failed, you can modify Python.py and make package working for other users later on if there are some problems. For example, along with package.py, you can also use patches and so on. Spack supports all that features. But there is one thing which you have to do extra. So if you will simply switch to the directory, it's not sufficient. You should also do it in the proper build environment. So, for example, for the previous example with a LibOSRM installation, that library depended on Boost, and you have to know where that Boost was installed. And Spack can tell you what build environment it uses with the Spack build-env option, with the Spack build-env command. And basically, to go to the concrete build environment, you can use Spack build-env and then run in bash with this concrete environment. So next part, reproducibility mechanisms in Spack. So it's an important, it's something which probably not everyone knows who uses Spack, but it's a very useful information. If you will go to the content of the folder where some package was installed, and you can get the path to that folder with Spack location command, you will see that. Well, not surprisingly, that for Boost, you will see include library, lib, include folder, lib folder, but also you will see a folder.spack. And that's some metadata. And actually, Spack also, when it's not only installs the software, it also supplies it with some metadata on the installation process. And let's take a look on this metadata on this .spack folder. So first of all, what do we see? We see that it has install manifest JSON file. And this is basically the information about all the files which are present in include and library folders. And it means this is the information about all headers, all libraries and so on, along with their hashes and so on. So then we have repos folder, and this folder, amongst all, this folder actually contains all the packages from the repository which were used to install this package. For example, it contains, if you will take a look here, you will see that it contains package.py for the Boost dependency. It contains package.py for zlib and all the patches which were used along with this package.py files. So you basically can also get knowledge about the environment which was used to install the package. Then you have something which built-env return, Spack built-env return. This is basically all the Spack environment, built environment for the package. Then you have the output, which was produced by Spack, by the installation process of Spack. So basically all that, in case of LibOSRM, it will be the list of all make outputs and make file outputs, all that stuff. And then you have fully concretized specs for the installed package in the YAML format. specs YAML file. We'll go back to this a little bit later. So now installation is the one thing, but besides installation, we also want to use our installed software. So what other commands does Spack propose besides this, those which we already considered? So the first one is find. Find is a command which basically allows you to check what can be used, what packages can be used, what packages are already installed. It's some analog to module avail in common HPC environments. And well, you basically use it in the following way. You tell Spack find and then use some spec. It shouldn't. And for example, here I find all packages which depends on all installed packages which depends on Python 3.7 or higher or below. Sorry. And here I find all packages which were installed with the option all3. Optimized packages. So, okay, this Spack find contains many options which allow you to show more details on the spec. For example, with if you will use this list of options, you will see the hash of the installed package, of the found package, the fully concretized spec for this package, also path where it was installed, and so on. So basically all detailed information, which you probably want to use or not, but all the details. So now, again, if you work with some extensible packages like Python, then you should use extensions instead of find. Usually you should use extensions instead of find. And for example, here I show how to find all packages installed for Python 3.9. So next part. Well, besides finding packages, we want to use them. And in order to use them, we should load them normally. And Spack has the command Spack load for doing this. And well, whenever you don't need the package anymore, you can use Spack unload. And yeah, when you work with extensions, you have to use instead Spack activate and Spack deactivate. For example, here I activate extension PyNumPy. So, but this Spack activate and deactivate stuff, they have some drawbacks, which are listed here. So now the next point, how to check the list of active packages. And actually, how to list packages which are loaded, basically. And actually, you can again use find for this purpose. So for example, here, well, and you should use find with the option loaded. For example, here I load the load OSRM library and try to list what packages will be loaded afterwards. And basically it loads a lot, not only libOSRM. If you want to load libOSRM on, it loads also all dependencies of libOSRM. But if you want to load libOSRM only, you can use the following way of loading package. The option only package. Again, if you use with Python extensions, you have to use extensions command, and it has option activate, which allows you to list packages which were loaded along with for the concrete extensible package. So besides installation, we are also sometimes interested in uninstalling software, and here it can be done with an uninstall command. And again, it has many options which basically do most things which you probably want to do, and I don't want to spend much time on this. You can later on browse through them. So the next important stuff within Spack is that it supports environments. It allows to create you something similar to Python virtual environments with PyPI. So in order to create an environment, you have to use command spackn. And the typical workflow for creating the environment is the following. You call spackn create, activate, then add some specs to your environment. So the list of packages which you want to use within an environment. Then you concretize this environment and install it. And whenever you do not need the environment anymore, you can use the command despactivate, which is analog to deactivating with virtual envs in Python. So now let's do the same what we've done with installed packages. Let's take a look what is created within the environment folders. And within the environment folders, by default, we will have the subfolder spackn with some additional .spackn with some additional metadata, which is not so useful actually in the case of environments. But the useful part is that in the environment, we will always have two files, Spack YAML and Spack log. Spack YAML file defines the logical environment, and Spack log defines the exec environment. And later on, it will be clear what does it mean. So let's take a look on the content of Spack YAML. Here is an example which will be generated by the previous commands. You have here the list of specs and view view true. Well, actually, yeah, I didn't tell you before about use. Use is basically the way to creating references to different libraries and executables and so on at the one place for all the dependencies of the environment, for all specs and dependencies of the environment. But if you will take a look on this environment definition, it looks pretty ugly, not so nice. Well, let's see, because the list of specs is somewhat polluted, a really long line, not so convenient to read. What can we do? We can basically edit this environment. And in order to edit environment, you can run spack config edit, and it will open this environment for you for editing, for further editing, if it is activated. And well, for example, the first what we can do with the environment to improve it, well, here, as you see, we installed Python with optimizations, the latest Python 3.9 with optimizations. And then all our extensions were installed with this dependency. We can do it in a slightly short annotation. In order to make it in a short annotation, you just have to define a matrix. You should have to use so-called matrices, which allows you to give this combinatorial Cartesian products, let's say, Cartesian products of the software, of the specs. For example, here in the you see the following information. Here we first install Python. We have spec for Python, for optimized Python, and then we define matrix where we list all packages which we want to install, and all of them will be dependent. Here we mark. Here we have this head for dependency notation, all of them will be dependent on Python 3.9 with optimization. What can we do next? Besides using matrices, we can use definitions. That's basically some. So the ugly part of this particular code is that we reuse Python spec twice, and it's not particularly safe. We usually want to use it in the single place, and we can do it either. And for that purpose, we can use definitions that are basically variables which we can further use in the definition of specs. And here we define the list of packages and define the Python version which we want to install, and the same example as before. We install Python, these packages, and tell that all of them will depend on the Python. Next stuff is that we can also enhance environment by some additional hints for Spack. For example, here I added the hint that concretization for the Spack environments should be done in the following way, that Spack tries to make the number of duplicated, not make. The Spack tries to not to install duplicated packages. So it will install only one version of Boost. It will install only one version of Zip, even if the concretization process for another packages required, prefers to have a different versions of Zip installation. So it will, in other words, in the installed environment, we will have only unique installation for each package. We can also tell the Spack that we want to use this environment to create singularity container, for example, and that's in the easiest way. It's like this. We just tell container in the format singularity, but you can add more details. What to use as a base for this container and so on. Last part, which I wanted to tell, that in the package in the environment, you can also define the preferences for packages to use. For example, sometimes we do not certain that we want to use optimized Python, or we want to use Python 3.9. Probably there exists another Python already installed in the system, which is better, which is already available, but it's not 3.9. And in this case, you can use like package preferences section, like on the example here. So next part is reproducing of the environment. The nicest part of the environment that they can be used to reproduce them either logically or exactly with the Spack log and Spack YAML files. So what I want to say that Spack and create commands allows you create not only empty environments, but it also allows you create environments from the available Spack YAML file. And if you use Spack YAML file, it will create a logical environment from the manifest, from abstract specs. But you can also use a Spack log file, which is the concretized environment, the concretized exact environment with the concretized number, with the concretized list of specs. And yeah, the comment is the same, but you should use the JSON log file, which is a JSON basically. So, but after both these processes, it's also recommended to forcefully concretize the environment in order to avoid different problems. So I will probably skip this slide. This slide is about stacks. stacks in Spack, and stacks are basically something which you can create with matrices. It's a combination with different versions of the same package. Next stuff is environments VS packages. Well, actually, you can use not only environments to create something like reproducible, logical installation process, but you can use also packages for this purpose. So in particular, you can use bundle packages. These are packages which give you a list of specs to install, a list of other packages to install, but they do not install something in particular. They just something similar to environments, just a list of just a list of other packages to be installed in a group.